Okay, so this is weekend topology seminar, and it's great pleasure to have Ellen Henke from Dresden University of Technology. And we are going to hear about fusion systems, linking systems, and punctured groups. So Ellen, please take it away.
Yeah, thank you very much for the invitation. So I will start with an introduction to the subject, and then I will talk about some joint work with Andrew Chermak, and then later about some joint work with Assaf, Libman, and Lynd. So yeah, I understand that for some of you this is probably quite boring, but I want to get through the background. So the motivation comes, of course, from finite group theory. And if I start with a finite group, then what is traditionally called fusion is just conjugacy of p subgroups. And so in particular, if you have two subgroups, P and Q of G, usually we want to look at P subgroups and G, then we can look at the conjugate of P under G and want to assume that's contained in Q, then we can look at the conjugation homomorphism from P to Q, which just does the normal thing. So this will be injective group homomorphism. Okay, and now the idea is to put the information we get that way kind of neatly together in a category, and that's the fusion category. So if S is a Sylow P subgroup of G, then we can conjugate every P subgroup into S. So for many purposes, it's just enough to concentrate on the subgroups of a fixed Sylow P subgroup G, and this is what we want to do now. But for this very elementary construction, I actually could also just assume that S is some P group of G. So and what I want to take then is the category with objects. Oops, this was, so the objects. Sorry. So Fs of G is a category such that the objects of Fs of G are just all subgroups of S. So I write this for the set of subgroups of S. And the morphisms in Fs of G between two subgroups P and Q. These are just the conjugation homomorphisms from P to Q, which we get from elements of G for which this works, so that's such that P conjugate under G is contained in Q. And we write this also as hom G from P to Q. So this is a category one can look at, and that's kind of the prototypical example of a fusion system. So abstract fusion systems, so perhaps I want to say here, we want to look at this category, but we also want to keep in mind that we have this P group S as part of the data. And this is also what we do when we look at abstract fusion systems. So that's, we fix here any P group, so some P group S, I should say. And then a fusion system over S is a category F, such that, as in the example before, the objects are all subgroups of S. And then the morphisms have kind of similar properties as in the example before. So first of all, they are all injective group homomorphisms. And of course, the composition in the category should then also be the same as the composition of maps. And then, okay, there's no group G around anymore, but I can still conjugate by elements of S. So I can look at hom S from PQ. And I want all these conjugation homomorphisms by elements of S to be contained in the morphism sets. And then there's this technical thing. If I have a morphism, so that's from P to Q, that's an injective group homomorphism. And if I now sort of restrict the image, then I get a map from P to phi of P, which I also call phi. And I can take the inverse maps, and I want both of these to be morphisms in F. So that is a fusion system, and usually one wants to look at saturated fusion systems, and there are some additional axioms hold. So I think more enlightening than giving you the precise definition is the example. So if G is a group, as a finite group, or could be even just some group, and P is a finite P subgroup, S is a finite P subgroup. Then, of course, this guy Fs of G is a fusion system. And it's saturated if S is a Sylow P subgroup of G. So these saturation axioms are really meant to model the situation where S is a Sylow P subgroup of G. I mean, it can happen that S is not a Sylow P subgroup and Fs of G is still saturated. But this is kind of the case in which we can show in a systematical way that it is saturated. Okay. So if you look at a saturated fusion system, then of course the obvious question is whether or not we can realize it in this way by a finite group G, the Sylow P subgroup S, and I call F realizable if F equals Fs of G for some finite group G. And some S and Sylow P of G. So these are kind of the standard examples, but then there are also some fusion systems which are not realizable, some saturated fusion systems, and these we call exotic, call F exotic if F is not realizable. So exotic fusion systems are kind of thought of as the exceptional cases. And indeed, at the prime 2, at least, they seem to be quite rare. Okay, what I wrote down here, I just realized it's not quite right. So there's only one known family of, so I should say, simple exotic fusion systems at the prime 2, because, I mean, similarly as for groups, we can also kind of glue fusion systems in many ways together to get fusion systems with different composition factors. So we need to restrict to the simple ones to be able to say something, but there's only one known family of simple exotic fusion systems at the prime 2, and these are the Benson-Solomon fusion systems, Sol Q, where Q is an odd. So this is a family of fusion systems, so whenever Q is an odd prime power, then we can build this fusion system, Sol Q, which is an exotic fusion system. So I will say more about that later on when I need it. Then at odd primes, there are many exotic fusion systems known, but still they seem to have a somewhat not too involved structure, too large structure, so still they appear somehow like exceptional cases. But there are some infinite families and there are also some small exceptional cases. So a general goal would be to get a better understanding of exotic fusion systems. So for example, the first question would be, of course, how many exotic fusion systems are, or how many simple exotic fusion systems. And yeah, so for p equals 2, it's actually the conjecture that this is the only family of exotic fusion systems at the prime 2. And for odd primes, I guess we don't have such a good idea what we are hoping to prove. But in any case, it would be interesting to see what kind of exotic fusion systems we can get there. Then if you look at exotic fusion systems, one can also think whether one can find some kind of measure how exotic they are. And some of the things I'm going to say later on go also into that direction. So first of all, let's go back to the basic stuff. So if one looks at fusion systems, the strategy is in principle that one wants to study in similar way as one is used to studying groups. So one wants to introduce similar concepts. So I've mentioned already that there's something like as a term of a simple fusion system. So first of all, I should say there's a natural notion of subsystems and of saturated subsystems. Yeah, so a subsystem would just be a subcategory, which is a fusion system over some subgroup of this P group S we are looking at. Yeah, and then such a subsystem is only a fusion system, but we are particularly interested in finding some which are also saturated. So that's one thing, and then there is also a relatively natural definition of normal subsystems. And for groups, normal subgroups generalized to subnormal subgroups. And well, if you have normal subgroups defined, then you just kind of the transitive closure of this normality relation to get subnormal subgroups. And the same thing we can also do here. We take also then subnormal subsystems. Okay, so if you look at normal subsystems, I mean, similarly as in groups, the trivial fusion system, so the fusion system of the trivial group, and the entire fusion system will always be normal subsystems. And if these are the only ones and they are different, when we call a fusion system simple, so simple fusion systems. And then one very basic concept. So it's difficult in general to look at normalizers and centralizers of subsystems, but if F is a fusion system over S, over P group S, and P is a subgroup of S, then there is something like a normalizer in F of P and a centralizer in F of P defined. So these are subsystems over the normalizer in S of P and the centralizer in S of P, respectively. So even if F is saturated, they are not necessarily saturated, but one can basically always arrange things such that they are. So if F is saturated, so if F is saturated and P is, in a sense, suitably chosen up to F conjugacy, so what I mean here is up to moving to an F isomorphic object. Yeah? So that would correspond to conjugation in the group if you look at a group fusion system. So one says F conjugation. So suitably chosen up to F conjugacy. Then the normalizer in F of P, the centralizer in F of P are fully normal, are saturated. So, and needs to have a property, or at least if it has a property, which we call fully normalized, that means it's suitably chosen up to conjugation so that we get saturated fusion systems here. So now if E is a normal subsystem of F, then also the centralizer in F of E is defined. And what we have also defined are several notions of products of a normal subsystem with some other P subgroup and also with some other substructures of F, some other subsystems, but this is more involved. So one cannot hope to get something in as much generality as one would in groups. Then also, if you're group theorists, perhaps you have heard about components and the generalized fitting subgroup. So this is also something which is known for fusion systems. So there's components and a generalized fitting subsystem. So this was introduced by Aschbacher, and there are several more concepts. So basically one can do many things as one is used to in groups, but things are always getting a little bit more technical and a bit more difficult to construct. And also some concepts are not defined. So you can, what's not defined, for example, is the centralizer of an arbitrary subsystem. So centralizers are only defined in special cases. So what's the motivation at all to study fusion systems? I guess different people have different motivations. So for me as a group theorist, one important motivation is that I want to get a new proof of a classification of finite simple groups. And Aschbacher announced a program here where he wants to first classify simple two fusion systems and then use this to deduce the classification of finite simple groups. So actually what he does at the moment, and that's already completed to a huge extent, is only classifying certain simple two fusion systems and redoing a certain portion of a classification of finite simple groups. But if one would kind of extend this, I mean, one could hope, I think, to, but it's a lot of work, of course, to classify all simple two fusion systems. And then one would in particular get a proof of this conjecture that the Solomon, or if it is true at all, that the Solomon fusion systems are the only simple fusion systems at the simple exotic fusion systems at the prime 2. Then other motivations come from modular representation theory. So traditionally, modular representation theory, they try to prove kind of some connections between the representations of normalizers of non-trivial P subgroups, which we call P local subgroups, and of the entire group. And many of the conjectures can be formulated in terms of fusion systems. So that's another motivation. Then some motivation comes from what P cohomology. So if G is a finite group and S is a Sylow P subgroup of G, then it is a classical theorem by Carter and Eilenberg, the stable elements formula, which says that the mod P cohomology, so the cohomology with coefficients in the field with P elements, is determined actually by the fusion system Fs of G. But there are also some more results. So for example, Quillen has stated some, has reformulated some properties about mod P cohomology in terms of in terms of fusion in the group. Yeah, and then one very important motivation is also the study of P-completed classifying spaces of finite groups. So Bausfield and Kahn introduced this P-completion functor, which many of you know, of course, much better than I do. And the Martini-Priddy conjecture says if you have two finite groups G and H with Sylow P subgroups S and T, then the P-completed classifying spaces, so BG P-completed, so homotopy equivalent to BH P-completed, if and only if the fusion systems are isomorphic in a suitable sense. So, and this one correct direction was shown by Martino-Priddy, and the other direction, the other direction was first used by Oliver using the classification of finite simple groups. So by now there's also a proof without the classification, and this uses fusion systems. So I will say more about that later. So before I get to some definitions, which I will not give in full detail in the abstract, I want to go back to the case of finite groups again. and show you some other examples. So we have this fusion system, which kind of captures a lot of the information we see about fusion, and also which we see of normalizers of non-trivial P subgroups, which we call P local subgroups. But one could also consider other categories. So if delta is any set of subgroups of S, then one can form the category T delta of G such that the objects of this category are just delta. And the morphisms in this category between two objects, P and Q, are just what we call the normalizer in G of PQ. So it's kind of a generalized normalizer. These are the elements G and G such that P conjugate under G is contained in Q. Or more precisely, one would have to say one takes the triple PQ G, that G is a normalizer in G from PQ, to distinguish the morphisms, the different morphism sets. Okay, so that's another category, and it's sort of, I mean, if you would take delta to be the set of all subgroups of S, then it in some sense contains more information than the fusion system. So observation. The morphisms in Fs of G from P to Q. These are, as I said, the conjugation homomorphisms, but one could also basically see them as, I mean, they are induced by elements in here, but we kind of identify them if the conjugation by such an element does the same on P. So what we actually do is we look at the right cosets of a centralizer in G of P. So perhaps I should write it like that. Yeah, so in some sense, so this category above it contains a bit more information. Okay, and now we want to form what we call the linking system. And here the idea is to look at a special object set, and then we don't factor out the entire centralizer, but we just factor out a part of the centralizer. Okay, so what is the set we want to look at? That's FSG to the C. These are the subgroups P of S, such that the centralizer in G of P splits as the center of P times some subgroup, which I write as CG prime of P. This is just to be some P prime subgroup. Yeah, so what I mean here, I take the P contained in S such that such a P prime subgroup exists, such that I can split it. But if it exists, it actually also turns out to be unique. So I can give it this name CG prime of P. And then it's a classical theorem by Alperin that if I look at the fusion system Fs of G, this is actually generated by the morphisms between things in this set. So I should say we call them the Fs of G centric subgroups. Okay, so this theorem of Alperin says if you look at the morphisms in Fs of G between P and Q, where PQ are Fs of G centric, then this generates already the fusion system. The generation is defined in a natural way. So, and now the category LSC of G is the category where the objects we just take the set fs of g to the c. And now if you look at morphisms in this category LSC of G between two objects PQ, so PQ and Fs of G to the C, then we know in particular that P can be split in this way. Yeah. So, and what I want to do, I don't want to factor out the whole centralizer as I do it above here, but I just want to factor out this P prime part. So I take this guy and factor out CG prime of P. And this is my category. And we call this also the centric linking system. So, and the centric linking system is interesting if one looks at P-completed classifying spaces. Because if I look at the P-completed classifying space of G, that's homotopy equivalent to the nerve of this category, and then P-completed again. So this means already that, I mean, the classifying space, first of all, seems to be a global object. Yeah. So BG, to form that, we would usually look at the entire group. But then we apply the P-completion. And then this says, if you look at the P-completed classifying space, we can actually describe it in terms of this kind of local category, this category LSC of G. So we have already boiled this down quite a bit. And so you can see probably that this centric linking system is already relatively close to the fusion system. Yeah. So basically it contains more information, yeah, because Fs of G is generated by this. I can basically can get it from this, yeah, because this projects onto the homomorphism set in Fs of G between P and Q. So, and the Martino-Prudi conjecture said that two P-completed classifying spaces are homotopy equivalent if and only if the fusion systems are isomorphic. And this kind of comes fairly close to this, but just not quite close enough. So there's an abstract notion of a centric linking system associated to a saturated fusion system. This is due to Brotolevy and Oliver. I will hint later on it what this is, but I will not give a proper definition. So let me first say that there is always such a thing. So that was an open conjecture for many years, but then Chermak proved that if F is a saturated fusion system, then there exists an essentially unique centric linking system. Associated to F. So as I said, Chermak proved this first, but then using some idea of Chermak's proof, Oliver also gave an alternative proof which uses some methods which he developed before with Proto and Levy, so some abstraction theory. Both proofs use originally the classification of finite simple groups, but the dependence on the classification was removed by Libman and Lynd. So the original proofs use the classification in a very structural way via some theorem on certain modules, so modules of groups, and basically then Libman and Lynd proved a group theoretical result, a module theoretical result, which removes this dependence. So, okay, so this theorem is very important, very interesting, at least for two reasons. So first of all, it means that there is something like a p-completed classifying space of a fusion system. Because, I mean, for groups, if we look at the p-completed classifying space, we can just as well look at the p-completed classifying space of a centric linking system. So we can now do the same for an abstract fusion system. There is this unique centric linking system, and we can look at the p-completed nerve of this. And then we also get a new proof of a Martino-Priddy conjecture. So let me just write this down. So if you have two Sylows, if you have two groups, G and H, with Sylows S and T, then so the direction I'm interested in is that Fs of G, if this is isomorphic to Ft of H, I want to argue that the p-completed classifying spaces are the same. And now the uniqueness part in Chermak's theorem says that there's a unique centric linking system. So unique means, of course, up to a suitable notion of isomorphism. So that means then, since one can show that these are actually centric linking systems, of course, in the abstract sense, that this is isomorphic to LTC of H. So they are in particular isomorphic as categories then. And then we know also that the nerves are homotopy equivalent. Then the same is true after p completion. But now we have this theorem of BLO, which says that this is just the p-completed classifying space of H, and this is the p-completed classifying space of G. And so we get that they are homotopy equivalent p-completed classifying spaces. So this would be then a proof of a Martino-Priddy conjecture without the classification of finite simple groups. Okay, so when I give these online talks, I never have any sort of feelings whether I'm going too fast or too slow and whether you can follow. So was this okay so far, or was it any
yes.
questions?
Yes, the pace is good. Yeah.
Okay. Okay, so now to motivate the abstract definitions, which I will not give in full detail, let's just make some easy observations. So I introduced these concrete categories above here. So what kind of properties do we have? So if I look in the category T delta of G, a morphism set would have this form. Yeah, and we can always include in this the normalizer in S of PQ. Yeah. And also we have seen that there's a surjection to the morphism set of S of G PQ, yeah, in the very natural way. So this holds for all PQ and contained in S. And a similar thing is true if you look at the morphism sets in the category LSC of G from P to Q. So since we are just factoring out P prime elements when we go from here to here, actually we still get that a set of P elements can be, is injectively mapped into this. And also we now just need to factor out a little bit more. So we have factored out already some P prime elements in the centralizer. Now we also factor out the rest in the centralizer of P, and then we get again the morphism in Fs of G from P to Q. So, and that's now the motivation which I want to use to give to hint on an abstract definition of a transporter system, which is due to Oliver and Ventura. So, and where linking systems are special cases of transporter systems. So if F is a fusion system over S, then a transporter system associated to F is a category T. such that the objects of T are some subgroups of S. So this is contained in the set of objects of F, which would be the entire set of subgroups of S. And then we are given structural functors from the category T delta of S to T. So if you recall, the category T delta of S, this here would be the morphism set between two objects. Yeah? And so we have this functor, and then we have also a functor to F. And they have several properties, which I'm not going to list all. So first of all, epsilon is the identity on objects. Yeah, so delta is a set of objects of T. So these two have the same object set. Epsilon is just the identity on this. And every object of T is an object of F, and pi is just the inclusion on objects. Okay, and then we also get that this epsilon is injective on morphism sets, which I've hinted with this kind of arrow here. And delta is surjective on morphism sets, which I've hinted with this kind of arrow here. And then several other axioms hold. So now a centric linking system is a transporter system T such that the objects of T are the F-centric subgroups, which I haven't defined, and then some axioms hold. So these F-centric subgroups just generalize what I defined before for groups with set F S of G to the C. So these are subgroups of S such that every F conjugate contained its centralizer in S. Okay, and then there are also some more general definitions of linking systems. So there's one definition due to Oliver, and also some early ones due to Broto, Castellana, Groda, Levi, and Oliver. I came up with a sort of bit more general, well, actually, no, more general definition of a linking system, which I'm going to use here. So a linking system over F is a transporter system T associated to F such that the object set is in a certain set large enough. So for the experts, that means that the centric radical objects are contained in the object set of T. And moreover, if P is an object in T and G is the automorphism group of this, so the morphisms in T from P to P, that's a group, then this has the property that the centralizer in G of OP of G is contained in OP of G. Here OP of G is the largest normal P subgroup of G. And that's a property which one looks a lot at in finite group theory. So one calls groups G with this property, one calls groups of characteristic P. Okay, and since this is such an important concept in finite group theory, this also gave me the idea that this is probably the right thing to look at if one wants to define linking systems. Or at least many things go right if one does it this way. Let's put it like that. So what goes right is that in some sense we can generalize the existence and uniqueness of centric linking systems to this more general case. So if F is a saturated fusion system over S and delta is, I say here, a suitable set of subgroups of S, meaning it fulfills some conditions which any linking system, any object set of a linking system would have to fulfill, then there exists a linking system L delta whose object set is delta. And it's a unique one up to isomorphism. And also the nerve of this linking system would be the same as the nerve of a centric linking system, which I denote here like that. Also, that can show that there's a largest set delta, which is in that sense suitable. The set which I call f to the s of f some centric subgroup. So I don't want to define this in detail, but so you get kind of a largest one always. And this set therefore plays an important role. And you can define the set just in terms of a fusion system F. Okay, now I introduced more or less transporter systems. So Chermak, when he proved his theorem about the existence and uniqueness of centric linking systems, actually looked at it in a different way. So he introduced a concept which is in some sense, well, not in a very precise sense, but well, equivalent to the concept of a transporter system. So not in a categorical sense, but it is sort of the same as a transporter system. So here is the definition. A partial group is a set L such that it has some properties like a group, but the product is not defined on. So we look at the product as a multivariable product, but the product is not defined on all words in L, but only on certain words. So we have a subset D of a set of words in L. And then we have product pi, which is only defined on these words. So this would be a partial product. And then we have an inversion. L to L. F goes to some element which we denote by F inverse. So this is an involutory bijection. And then some axioms hold, which are group-like. Yeah, something like associativity holds. And then the product should be defined on the words of length 1, which I identify with L. So pi restricted to L is the identity on L. And then the empty word is in D. And if I look at pi under the empty word, this is like an identity in a certain sense. So we get some group-like axioms. So the easiest example, if G is a group, then G is also a partial group where the product is just defined on all words in G. And the product is just the usual product in G, now looked at as a multivariable product. Okay, that's of course the first example which comes to mind probably, but it's also not the most interesting example. I mean, we want to look now at something which is again sort of p-local. And actually we look now at something which is very close to this category T delta of G, which we looked at before. So if G is a finite group, S is Sylow P subgroup of G, and delta is a set of subgroups of G, and we assume some so we assume this property that's closed under passing to G conjugates and overgroups in S, some technical property, then we can define a partial group. And by the way, for T delta of G to be a transporter system in the sense of Oliver and Ventura, we also want this technical property to hold. So now we can define a partial group. So as a set, we just take all F and G such that there exists some P in delta with P conjugate under F is contained in S, which by this property just means P conjugate under F is in delta. And then on which D do we want the product to be defined? So we take the tuples F1 up to Fn, such that basically if we look at these Fi as some, I mean, they lie then in some transporter set. So we want them to lie in some transporter set, and we want the product to be defined in this category T delta of F. That's the idea. So if there exists P naught, P1 up to Pn in delta, such that Pi minus 1 to the Fi, sorry, the other way around. Pi minus 1 conjugate under Fi is Pi for I between 1 and n. Okay, and then the product is just the restriction of a usual product on G, and the inversion is just the restriction of the usual inversion, and this gives me a partial group. Yeah, and as I said already, this is closely related to the category T delta of G, as you hopefully can observe. Also, one thing to observe, if the trivial group is in delta, then L delta of G is just G and therefore a group. Yeah, because then here I can just take here P to be the trivial subgroup, and this is always true. So L delta of G would be G, and also the product would be defined on all words. Okay, I'm just looking at the time. I think I'm a bit slower than I thought I would be. So in partial groups, since they are so group-like, there are natural notions of partial subgroups. So there's are subsets which form partial groups again, then of subgroups, which are subsets which are actually groups. Yeah, so the product is defined on all words in a subset, and also of partial normal subgroups. So these are partial subgroups such that if a conjugate of an element in this partial subgroup is defined, then it is again this partial subgroup. So we have a natural generalization of normal subgroups. Okay, and now we have the definition of a locality. So that's a triple L delta S, such that L is a finite partial group. Then S is a subgroup of S, so a subset, which is also a group. And it's a P subgroup, yeah, and it's maximal among all such P subgroups. So it's like a Sylow P subgroup. And then similar properties hold as in the example before. So basically, the product should be defined on words which have a property like this. And then there's a natural definition of a fusion system Fs of L. And as Chermak proved, then these localities correspond to transporter systems. So more precisely, if F is a fusion system, then the localities of fusion system F correspond to transporter system associated to F. So actually, one can form for such a locality similarly as for groups such a category T delta of L, and that's the transporter system. So going the other way around is slightly more tricky. So one basically looked at the isomorphism in this transporter system, and then one has to identify some to construct a partial group. Okay. Oops, I just realized. I think I skipped something here, which I didn't want to skip. Sorry, just go into my original notes. Yeah, so the theorem I proved together with Andy Chermak is now if we take a linking locality, so that means just T delta of L is a linking system. But one can also define that purely in terms of a locality. Then there's a one-to-one correspondence between partial normal subgroups of L and normal subsystems of F. And actually, there are also a lot more concepts in linking localities, at least in special cases. And then we get also a more comprehensive dictionary. So why is this interesting? So first of all, we get new proofs of known theorems of fusion systems, but we also get some new theorems on fusion systems. So for example, we can now define products of normal subsystems, of two normal subsystems or several normal subsystems, which before was only done in very special cases by Aschbacher. We also can define certain other products, which are more technical to describe. And I can also define centralizers of subnormal subsystems. So this is something, I mean, I said before, we can define centralizers of normal subsystems, this was due to Aschbacher, but now I can also define centralizers of subnormal subgroups. Another motivation for me is that I think it gives probably a better framework for at least a part of Aschbacher's program, probably not for all parts, but at least for some parts. And I think this is probably also a better framework to study extensions, but this is also still something which is very much work in progress. Okay, so I was asked to talk about punctured groups. Now, this is a project together with Assaf, Libman and Lynd. So I want to spend the rest of the time to talk about that. So what is a punctured group? To motivate that, I just want to remind you of what I said. If G is a group, S is Sylow P subgroup of S, and we take the subset delta of subgroups, and we have the identity subgroup in G, then L delta of G is a group. So one can see more generally, if L delta S is a locality and the identity subgroup is in delta, then L is a group. So the partial product on L is then defined on all words in L, and the partial product becomes an actual product on L, which then makes L into a group. Similarly, I said localities and transporter systems are equivalent, so I could similarly look at a transporter system where the identity subgroup is an object, and then I could look at the automorphism group of the identity subgroup. That's a group. I can more or less embed S into this via this functor here. And then if I identify S with a subgroup of G, then I get that this transporter system is actually isomorphic to T delta of G. So in that way, one sees that basically if one is an object in a locality or a transporter system, then this locality or transporter system more or less corresponds to a group. Okay, so what we look at now, if we consider punctured groups, is we look at the situation that the identity subgroup is not a subgroup, is not an object, but we come as close to it as we can by saying that we take all other subgroups to be objects. And we do this both for localities and for transporter systems. So we call a locality a punctured group if all non-trivial subgroups of S are objects, so delta, and we call a transporter system T punctured group if the object set of T is the set of all non-trivial subgroups. So I just realized that one thing I didn't say clearly. I said that there's this one-to-one correspondence between localities and transporter systems. So actually, if I take this one-to correspondence, then if a transporter system T corresponds to such a locality L delta S, then delta will always be the object set of this transporter system. Okay, so that's the concept of a punctured group. And actually that a punctured group exists means basically it comes very close to coming from a group. So if the identity is a subgroup, then Fs of L here is, of course, if L is a group, is a fusion system of a group. And if T is now a transporter system associated to F, then also F would be basically Fs of G if I identify S as a subgroup of G. So that the identity is an object means basically that the fusion system comes from a group. But punctured groups could also exist for exotic fusion system. And the question is now, if F is a saturated fusion system, is there a punctured group associated to F? And you can probably guess now already that the answer is yes, if the fusion system is a fusion system of a group. But for exotic fusion systems, it's not so clear whether this is the case. But actually, the answer will always depend on F. So one cannot give a general answer to that. One really has to look at cases here and very concrete fusion systems. But let me first make some very easy observations. So I said already, if we look at the fusion system of a group, then we always get a punctured group. So if F is Fs of G, then I can take the set delta to be the set of all non-trivial subgroups of S. I want this to be the object set of a punctured group. And as a punctured group, I can just look at L delta of G, or similarly at T delta of G if I prefer to look at a transporter system. And this is then a punctured group associated to F. Okay, so that's the first easy observation. So if a fusion system comes from a finite group, then there's always a punctured group. So next comes a condition which says that there is no punctured group. So if F is a saturated fusion system and there exists a punctured group, then one can see that actually if I look at this normalizer in F of P and I choose P suitably up to conjugation, such that the normalizer in F of P is saturated, then this is always realized by a finite group. So if I look at a locality, then I would have to look at the centralizer here, at this normalizer here, which is basically defined as in groups. Just that one has to be a bit more careful because conjugation is not always defined in localities. Yeah, but if a conjugate of P under F is defined and equal to P, then we say that F is in the normalizer in L of P. And that's always a subgroup of, if P is an object in a locality, which it would be if this is a punctured group and it's a non-trivial subgroup, and that's always a finite group, and it realizes this normalizer. So if F is saturated, and there exists a non-trivial subgroup such that the normalizer in F of P is exotic, then there can be no punctured group associated to F, because otherwise in this punctured group I could look at this normalizer and see that it realizes the normalizer in F of P, and then it would not be exotic. And similarly, I could do it for a transporter system. I would then take it out, look at out T of P and see that it realizes the normalizer in F of P. Yeah, so what I mean here is actually that P is suitably chosen up to F conjugacy so that the normalizer in F of P is saturated. Okay, so that's a condition under which I can see that no punctured group exists. Then there's also one more case where I can see easily that a punctured group does exist. So if F is of characteristic P-type, so that means basically that any saturated normalizer is realized by a finite group G such that this magical condition here holds, then that means that this set F to the S, which I said is the largest possible object set of a linking system, is the entire set of non-trivial subgroups of S. And then I can kind of glue all these groups G here, which realize some normalizer together to get the largest linking system associated to F, and that will be a punctured group. So in that case, it's also easy to see that I get a punctured group. And now we considered many examples of non-exotic fusion systems. And for odd P, the interesting thing is that in all the examples we looked at, we found that either this property star holds, so we know that no punctured group exists because some normalizer is exotic, or we know that it's of characteristic P-type, so we are in this case here, and that means that the largest linking system is actually a punctured group. So I listed here several cases we looked at. Yeah, I think because of the time, perhaps I don't go into too much detail, but if you're interested, I can say a bit more about that afterward. So at p equals 2, we have only this example of a Benson-Solomon fusion system, at least if we restrict attention to simple fusion systems. And here the story is actually a bit more interesting because neither of this property star holds. So where every normalizer of a non-trivial subgroup is realized by a group, but it's also not of characteristic P type or characteristic 2 type in this case. So one really has to be more clever to see what happens. And actually the story is also quite interesting because for some Q, this is real. This punctured group exists. So basically for the smallest Sol Q, a punctured group exists, but for the larger ones, it doesn't. So let me say a bit more about this fusion system Sol Q. How does it look like? So it is a fusion system over the Sylow subgroup S of spin 7 of Q. And also spin 7 of Q occurs as a subsystem. So more precisely, the center of S has order 2, and all involutions are conjugate to F, so they are all conjugate to this central involution Z. And the centralizer in F of Z, so Z will be the only conjugate of Z, such that the centralizer is actually saturated. And the saturated centralizer is realized by spin 7 of Q. So we see actually spin 7 of Q. So it seemed to be a very natural question to ask whether there is a punctured group where we can actually see spin 7 of Q inside as this normalizer, or we could also call it the centralizer because it has only order 2. And the answer is actually not so easy. So first of all, I should remark that we get a fusion system to every odd prime power Q, but in some cases we get the same fusion system. So basically we get the same fusion system if the two-adic variation of Q square minus 1 and second Q tilde square minus 1 are the same, then the Solomon fusion systems are the same. So in particular, if you look at the smallest fusion system, Sol 3, this is a fusion system over a 2 group of order 2 to the 10. Then this is also, it's the same as Sol Q, where Q is congruent plus minus 3 mod 8. And we showed now that there exists a punctured group associated with Sol Q if and only if Q is congruent to plus minus 3 mod 8. So in other words, to the smallest Benson-Solomon fusion system, there is a punctured group, and to all the larger ones, there is not. So and for the smallest, we could more precisely construct a punctured group such that the centralizer in L of Z is spin 7 of 3. And to do that, we basically start with a linking system on a certain set of objects, and then we try to glue things in to make it larger so that we eventually end up with punctured groups. And Chermak introduced a procedure which he also used in this proof of the existence and uniqueness of centric linking systems. And this is basically what we use here. So it's a constructive proof where we really need to look very much into the structure of Sol 3. So, okay, what's interesting is we get here spin 7 of 3 as a centralizer. But of course, it's also Sol Q for some other Qs. So a question which so far we have not answered is whether we could also get a punctured group where the centralizer is spin 7 of Q for some different Q. So the honest truth is at some point we just couldn't be bothered anymore to spend more time on that. I think that the answer is probably within reach, and my guess is, so my intuition is here that the answer probably depends on the Q. So that's, again, I think, probably a relatively interesting story to look at. So for the larger ones, we want to prove non-existence. Just seeing I'm already over time, I think. So perhaps let's just say, I mean, again, of course, we use some combinatorial arguments, but we need also some way of controlling the structure of a punctured group, assuming that it exists. And we develop some signalizer functor methods for that. So the idea is that we use this to control the OP prime of G if G is a centralizer of the central involution. Yeah, because we know that if you look at the centralizer, one can easily show that this is the extension of spin 7 of Q tilde for some Q tilde by some field automorphism of odd order. So we know basically G modulo OP prime of G, or we know the candidates for that, but controlling OP prime would be a priori difficult. And signalizer functor methods is something which is used in groups, and it's actually even easier in these localities because they are just local objects. So it was just, I mean, we just had to see the right thing, and then it's relatively easy to prove. There's no really difficult group theory involved. Okay, yeah, perhaps one thing to say last very quickly, to give some motivation, we also showed, which means really Assaf, Libman showed, that if a punctured group exists, when there's something like sharpness of a subgroup decomposition of F, so some cohomological result. Okay, I think I should stop here. Thank you for your attention.
Thank you very much, Ellen. Any questions for Ellen?
I have one. If
yes,
I may.
yeah.
It's actually the opposite of its also fusion systems. Is there such a thing as a punctured peer group?
A punctured what?
A punctured peer group. So if the fusion system is nilpotent, then I understand that every P subgroup is subcentric. But
yeah, I think then it's even realized by a finite group, right?
Right, but yes, but I mean, suppose you have a punctured group where all the automorphism groups are peer groups, then can you say that the fusion system is nilpotent?
I would think that is, yes, I think that has a punctured group. So that would also mean that the automorphism group of every P group is a fusion system of a P group, right? So yes. I think it follows basically from Alperen's fusion theorem then, because by Alperen's fusion theorem, the fusion system would be generated by automorphism groups of certain non-trivial subgroups. Now you know all these automorphism groups are P groups, so really that means also that they're all, I mean, because of a special nature of these subgroups, so these are centric radical subgroups, they all have to be, the only centric radical would be S itself, yeah? So it would be the fusion system of the normalizer of S, but this would be the fusion system of a P group. So therefore it would be the fusion system of a P group.
Right, okay. Okay, thank you. That's interesting. It's related to characterization of nilpotent blocks. So if you applied that to block theory, it might say something about which blocks are nilpotent.
Oh, okay.
Okay, thanks very much.
Any other questions?
I have a question too.
Yes.
This is mostly something I'm confused about.
Yeah.
So you define the transporter systems for fusion systems.
Yeah, guess, well, not properly, but yes.
Reverse definition. But those will depend on the kernel. Like it will be extension of the fusion system up to certain quotienting out morphisms. So there much more general.
Yes, so it is actually much more general than a linking system. So for a linking system, we want to look at special cases. And yeah, so there's no hope to get something like a uniqueness result for transporter system.
That's one question I had. Second question. When you said the punctured groups exist for finite groups, you based it on the existence of the transporter system for finite groups. So is that why they exist? Because the punctured group should be more like a linking system rather than a transporter system for a finite group.
No, actually, I mean, also for the punctured groups, we can show that there can be several. So, particularly, we looked at these Ruiz-Varel examples over. I mean, they classified groups over extra special groups of order p to the 1 plus 2, where the and exponent p. So, and for the prime 7, they found exotic fusion systems. But also for p equals 3, the story is more interesting because some sporadic examples crop up here, some sporadic groups. I don't remember right now which ones. And we actually look at these and also classify the ones which restrict to centric linking systems, and we find that they are not unique. So there are several cases there. So there's always, of course, a subcentric linking system, but there are also other punctured groups. So for punctured groups, we cannot get something like uniqueness.
Okay, but for the existence for the finite groups, do you use a particular result about transporter systems? Why the?
No, it's actually just this. I try to give this here. It's just this very elementary. Okay, that's too far, I think. It's very elementary construction. I was probably a bit quick here because I was running out of time. So you just look at these. I mean, if you look at it as a transporter system, then you just look at this category T delta of G, which I defined before, and just take delta to be the set of all non-trivial subgroups, and that would be a punctured group. But of course, also here for different groups, you could have get different punctured groups.
So this is as a partial group, it's the transporter system, but is a category transporter system or a linking system?
Yeah, if you look at the category, you take the T delta of G, you take delta, the set of subgroups, and as morphisms, these transporter sets. Then, of course, I mean, if all the subgroups are centric, or non-trivial subgroups, then you could, of course, also take the centric linking system that would also give you a punctured group. But this works, of course, only in a special case that all non-trivial subgroups are centric. But these things, of course, happen.
So for non-trivial P subgroups, what you will be quotienting out the morphism set of transport?
Non-trivial, I mean, usually I will not quotient anything out, yeah? So usually I would just take this, yeah.
Okay.
So, I mean, I would need to have some special conditions on this object set to be able to quotient something out properly. Yeah.
And for L data G?
Yeah, so if oops, what is this? So if this delta is fs of g to the c, then I could, of course, also quotient something out. But this does not work in general if I want to construct a punctured group.
I see. So for the family of non-trivial P subgroups, you don't have a similar L data construction. Is that?
Yeah, exactly. Yeah.
Thanks. That's it.
Thank you.
Thank you. Thanks.
Okay, any other questions for Ellen? Okay, so if not, let's take the speaker again. Thank you very much, Ellen.
Thank you for the invitation.
Thank you very much.